Now that we understand the high-level idea behind AdaGrad, let's discuss mathematically what it means. So let's say we have a lot of parameters theta. First, we create an accumulator. So this accumulator is going to help us allow our gradient descent to have adaptive learning rates. So let's set all of our accumulators called S to 0. And then for each training step, first we compute the gradient, then we will compute this updated SI accumulator by adding the previous SI with the current gradient squared. So please note that if compared to the previous velocity equation, where there was a beta decay hyperparameter, this formula over here does not have any decay parameters. This means that Si continues accumulating as we continue gradient descent, which means that as we continue to have gradient descent, this becomes very, very large. So what is the adaptive learning rate formula? It is basically, as we have mentioned earlier, alpha divided by square root of the accumulated sum of gradients. Now this small epsilon is here to make sure that we do not divide by 0. So basically, let's try to interpret what this means. It means that if we have very large frequent updates, you want to make sure that we decrease the learning rate for that parameter, because you don't want to overshoot the minimum by taking steps that are too big. Meanwhile, for small gradients, let's say if we have taken a lot of steps already, you want to make sure that you take larger steps now because you still have not reached the global minimum. So by dividing by smaller or larger square root Si accordingly, it will affect how our learning rate progresses. So the main pitfall of this algorithm is that the accumulated sum of gradients is always increasing. Because S always increases, the learning rate for every single parameter will decrease over time. So if you look at this cluster over here, as we approach the global minimum, the steps taken become much, much, much smaller until it seems to effectively halt before ever reaching a good minimum.